Good morning, students. Today we introduce the operating characteristics of queuing model MM1. So, how do we analyze the model? By using some tools and techniques is the interest of this class. Because steady state solution of the model derived in the last class. Steady state solution not only the main platform to the model. We need some characteristics. Characteristics like what is the busy period of the system? What about the ideal time of the system? How many number of customers in the queue? What is the waiting time of customer? Right? So these things are top priority for analyzing the model. So this class we will see that the operating characteristics, right? So before the operating characteristics, a small recall related to the model. The last class we are talking about a single channel facility or one queue one service facility. So arrival entered into the system. Before going to the service, some of the people are waiting for the required service, so that there is a queue line. Okay, from the queue line the service station selects a customer in a single mode. After the service he exit from the system. Okay, right. So in this one queue one channel model, M representing, what is the M here? M is the queue, the arrival distribution is a Poisson. The second M stands for, what is the second time here? That is the inter arrival times is exponential. The number of service channels, how many service channels here? Only one service channel. Okay, and the capacity of the system may be finite or infinite, but in this model we fixed at finite. Okay, the queue discipline first in first out, right? So here we talk about M denotes Poisson arrival and the second M denotes Poisson departures or exponential service times. One denotes single server, capacity of the system infinite, as well as first in first out. Okay, right. Now whenever the arrivals in a random nature, its arrival distribution is P&T is equal to e power minus lambda t whole power n by n factorial, where n is equal to 0, 1, 2, etc. so on. So the arrivals of customers in the system, in the queuing system, is always a Poisson process. Here lambda denotes the arrival rate. Okay, once they entered into the system, now the question stands for what about the service times or inter arrival time. You know that what is the inter arrival time? The successive arrivals at successive time periods is called inter arrival time. Suppose T1 be the first customer entered in the system. Now T2 stands for, what is the T2? Capital T2, the first and second customers enter successively in the time periods. Okay, so that is called the inter arrival time. That is already discussed in the last class. We derived its probability density function is an exponential. Form stands for f of x is equal to, okay, sometimes they are writing instead of f of x f of t. Strictly speaks f of t is right. Okay, f of t is equal to mu into e power minus mu t, where mu is a service rate or inter-arrival rate. By using the definition of mathematical expectation and variance, you can derive it to the mean is 1 by mu and variance is 1 by mu square. How do you find expectation of x here? The expectation of x is equal to integral over the range of x into f of x dx. What is the range here? Some 0 to infinity, looking like that. Here instead of x you can write the t is greater than 0. Okay, good. That is called the inter-arrival distribution or service time distribution. That is also known to you, right? Now we started with the operating characteristics. Okay, what are the operating characteristics? How do you find that? First of all, the probability of q size which is greater than some particular value. That particular value let us consider as n. Suppose there is a 140 members in the queue. They are waiting for the service. Good. Now my interest is how many members more than 100. That is my interest. Okay. So 140 members in the system, for example, right? My interest is how many members more than 100. So here 100 is equal to n. 100 is equal to n. So the queue size greater than or equal to n. Okay, that is probability of the size of the queue greater than or equal to n. Okay, now we need to calculate its probability function. What is the probability function? Summation k is equal to starts from n. Okay, k is equal to n to infinity pk. Generally we called pn. Pn representing the probability that there are n customers in the system, n units in the system at a time interval 0 to t. Because of steady state solutions, the time interval as t tends to 0, t will be removed from our model. Okay, so it is a independent of time. That is the reason. Okay, instead of n, just we written as k. Okay, right. Now we know that what is the steady state solution? The steady state solution, okay, is equal to, just you can see, this is rho power n into 1 minus rho. Pn is equal to rho power n into 1 minus rho. Instead of n, what we are writing right now? K. Okay, so that is equal to rho power k into 1 minus rho. Of course, this equality removed from your nodes. Okay, that is now 1 minus rho. It is a constant with respect to summation. Okay, summation k is equal to n to infinity, okay, rho power k. Rho power k. Okay, right. Now by simplification of the above equation, 1 minus rho summation k is equal to n to infinity rho power k into, we multiplied with rho power n, and also the same thing removed, rho power n minus 1. Introduced rho power n and removed rho plus n, so that the equation doesn't change, it remains constant. Are you okay? Right. Now this rho power n is independent of the summation, because summation running on k but not n. Okay, so this rho power n taking outside. Okay, now summation k is equal to n to infinity rho power k into rho power minus n. Okay, now the base is common for both the terms, so that we can write as rho power k minus n. Rho power k minus n. Now that summation running from k minus n, see that wherever the power is there, that will run for k is equal to n to infinity. Here what is the power right now? K minus n. Now that summation run from k minus n is equal to 0 to infinity. To infinity. Agreed? Right. Now see that k minus n is equal to, say, x. So it stands from x is equal to 0. So that summation running from x is equal to 0 to infinity rho power x. Rho power x, because put x is equal to k minus n. Okay na? Now expanding this summation, put x is equal to 0, rho power 0 is the 1. Put x is equal to 1, rho power 1, x is equal to 2, rho square, x is equal to 3, rho cube, etc. so on. What it could be, of course, it is nothing but sum of infinite geometric progression, geometric series. Okay, now what it could be, the common ratio? Common ratio is equal to t2 minus t1, t2 by t1. So rho by 1 or rho square by rho, so common ratio is equal to rho. So what is the sum of infinite GP here? That is 1 by 1 minus rho. Now 1 by 1 minus rho, here 1 minus rho, both are cancelled, finally remaining rho power n. What is the rho here? Lambda by mu whole power n. Lambda by mu whole power n. Why should I am derived here? Suppose in our practical examples or practical problems, how many customer, what is the probability that the customers existing in the system more than 20? More than 20. So we calculate probability of the size of the queue greater than 20 is equal to rho power 20 is equal to lambda by mu whole power 20. Lambda is called the arrival rate and mu is called the service rate. We can calculate. So my interest is how many customers more than 100 right now. Okay, so instead of 100 we can write n. Instead of 100 we can write n. Are you agree with my point? So what is the size of the queue greater than or equal to n is nothing but rho power n. This is one of the operating characteristic we need to find. Okay, right. Second one, the average number of customers in the queue. Sorry, here there is a small notational inconvenience, that is equal to LS. You remember this, LS, not LQ, because I am talking about the system. So the average number of customers in the system. Please the students right now note this point. This is not LQ. This is LS. By somewhere typical mistake occurred, you just check it. This is LS notation. Okay, what is that? Expected number of customers in the system. Expected number, expectation is nothing but the mean of the distribution that we done in many number of times in our previous chapters. How do you find expectation of a random variable x? Expectation of x is equal to, okay, the random variable taking the realized value, its probability mass function and all possible values of the random variable, that we can written as sigma x is equal to 0 to infinity x into p of x. X into p of x. Are you agree with my point? X into p of x, right? So you find in a random variable theory, in a distribution theory, expectation of x is equal to sigma x is over the range of x into p of x. The same thing here also, expected number of customers in the system. Expected number of customers in the system. Are you okay? Now how do you find the expected number? That is expectation of n. Instead of x there is a n. That is summation where over the range of n into p of n. P of n stands for p of x, probability function. That probability function in our queuing theory is steady state solution. In queuing theory is steady state solution. Understood my point here? Right. Now n over the range of n takes the minimum value is 0. There is no customer or one customer or two customers, it's going on, because in the steady state solution Pn is equal to what is the Pn? Rho power n into 1 minus rho, where n is equal to 0, 1 to etc. so on. Agreed. So now we write n is equal to 0 to infinity. 0 to infinity n into p of n. Suppose this summation is expanding, n is equal to 0. Put n is equal to 0. 0 into p naught. So 0 into p naught is multiplied with anything 0. So that the same thing also we can write n is equal to 1 to infinity. Okay, 1 to infinity. Okay, n into p of n. Both the terms are valid in our practical problems. Okay, right. Now simplification and make some mathematical application. N is equal to 0 to infinity n into, what is the Pn here? Pn is nothing but rho power n into 1 minus rho. Here 1 minus rho is a constant with respect to summation taking outside, right? So summation n is equal to 0 to infinity n into P of n. Right. Now again the same term, here rho power n is there, we can written as rho into rho power n minus 1. Okay, so that rho is constant with respect to this summation, just we take outside. So n into rho power n minus 1, n into rho power n minus 1. Agreed, right? Now rho power n, for example rho power n or x power n, that function we differentiated with respect to x. D by dx of x power n is equal to n into x power n minus 1. Yes or no? So just you think about this term is nothing but d by d rho of x power n. Instead of x there is a rho power n. Can we write this term? Okay, so this term stands on the differentiation of the function rho power n with respect to rho. These two terms, that is only the crucial for this point here, right? Okay, now the differentiation. Now the differentiation summation both are interchanged. Now the summation is expanding. Put rho is equal, n is equal to 0, rho power 0 1. Put rho x n is equal to 1, rho power 1. X is equal to n is equal to 2, rho square, etc. so on. Are you okay na? Now what it could be? Again sum of infinite GP. What is the value for this here? 1 by 1 minus rho. 1 by 1 minus rho. Are you okay na? Now that term differentiating with respect to rho. How do you differentiating? The differentiation of this quantity is 1 by 1 minus rho square. 1 by 1 minus rho square. You know that the differentiation of by using product rule or quotient rule, you will get as 1 by 1 minus rho square. You can observe here 1 by 1 minus rho square, here 1 minus rho. 1 minus rho, here square term cancel. Finally remaining, what is remaining here? Rho by 1 minus rho. What is the rho right now? Rho is nothing but lambda by mu. Okay, 1 minus lambda mu in the denominator. After simplification by taking LCMs etc. so on, you will get the final term is lambda by mu minus lambda. Lambda by mu minus lambda. What is the lambda right now? Lambda is the arrival rate. What is the mu here? Mu is service rate. Are you okay na? Right. Good. So the expected number of customers in the system, okay, LS is equal to lambda by lambda minus mu. Agreed? Okay. Second operating characteristic. What is the second operating characteristic here? The average number of customers in the system. I said the point is very clearly, this is not LQ. Just the students make it is as LS. S system stands for S. Q stands for Q. Right? So here the expected number of customers in the system, so that you can written as this is LS. Agreed? Okay. Now coming with the average number of customers in the queue. Here you can write LQ, not LS here. Just I made a small typical problem. There is a LS, here LQ. Dear students, keep this point in your mind. Don't forget. Okay. This is LQ. Agreed my point? Because it is a queue. So the average number of customers in the queue. Right. So let us say the size of the queue is equal to M. By using the mathematical expectation definition, expectation of M is equal to summation over the range of M into P of X. P of X stands for the steady state solution of the system, that is equal to N. You remember the fact this m is nothing but n minus 1. Why? Because suppose the queue size is the n, right? Suppose in the system there will be the n customers, right? One customer is already availing service. So how many customers existing in the queue? N minus 1. That n minus 1 we denoted by m. Here I am writing where m is equal to n minus 1 being the number of customers in the queue excluding the customer which is served. One customer existing in the service platform. Okay, so how many customers existing in the queue? Only n minus 1 only. That n minus 1 we may written as m only. Are you okay na? So instead of m we can write n minus 1. Okay na? Right. So whenever m is equal to 0, the summation running right now. So m is equal to 0, which implies m is equal to n minus 1. Right, which implies n minus 1 is equal to 0. Why? Because m is equal to 0, so that m is equal to n minus 1. N minus 1 is equal to 0. This 1 taken the right side, n is equal to 1. So that our summation running from 1 to infinity instead of m is equal to 0 to infinity. Instead of m is equal to 0 to infinity, our summation running from n is equal to 1 to infinity. Why? Because in the previous step we run the summation on m. In the second step, we run the summation on n. Are you okay? So n minus 1 into p of n. Agreed? Right. Now we multiplied separately with respect to pn. So summation n into pn minus summation n is equal to 1 to infinity pn. We apply the summation and multiplied with pn. Okay, now the students, just you think about it. This is equal to is nothing but the expected number of customers in the system. The previous technique, just we observe it. What is that? This is equal to the expected number of customers. The expected number of customers. That same term we measured n is equal to 1 to infinity n into p of n. So this is nothing but the expectation of n. What is the expectation of n? That is already find that row by 1 minus row. Row by 1 minus row. Now coming with the second term. What is the second term? Summation n is equal to 1 to infinity na, right? So here one term, first term, put n is equal to 0. This row power n stands for p0. Sorry, pn stands for p0. So n is equal to 0 we included here. N is equal to actually 1 to infinity. Right? Now my interest is that summation is running from 0 to infinity. I want to make it. So we introduced here one term p0 and subtracted p0. Agree with my point here? So that summation running from n is equal to 0, the same term subtracted. Are you agree with my point here? Right. Now here actually n is equal to 1. My interest is this summation I want to make to run n is equal to 0. What I have to do that? We introduced p0, adding p0, subtracting p0. Now that adding term again taking into my summation. So this n from 1 to run, that running now starts from 0 to pn. Okay na? Minus pn. Agree with my point? Right. Now here the same term stands for summation n is equal to 0 to infinity pn. What is that? It is the probability function. Sum of the probability is always 1 minus this p0. What is the p0 here? The initial probability that is already calculated in the previous lecture. That is 1 minus rho. Okay, so 1 cancel. Now there will be minus rho. Agreed? Right. Now by taking the LCM, taking common is the row and taking the LCM 1 minus rho. After the simplification, After the simplification, you will get as 1 minus 1 minus rho, minus 1 plus 1 cancel, negative into negative becomes positive, so rho is here, rho into rho multiplied as rho square by 1 minus rho. What is a rho? Lambda by mu. Okay, now substituting rho value as a lambda by mu, now what we get here? Lambda square by mu into mu minus lambda. Mu into mu minus lambda. So mu into mu minus lambda representing, what is the mu into mu minus lambda? That is equal to LQ. LQ is nothing but the expected number of customers in the queue. The previous one LS. LS representing the expected number of customers in the system. What is the difference here? In a system there are n customers totally. In the queue there will be n minus 1 customers. That is only the basic difference. In a system n customers, in a queue n minus 1 customers. N minus 1 customers. Agreed with my point, right? So system we denoted as LS. In queue we denoted as LQ. Okay, so we derived the operating characteristics of the queuing model. One is more than n units in the system. Second one, the expected number of customers in the system. Third one, the expected number of customers in the queue. Okay, right. Now once the customer is waiting for the service, naturally that waiting time is in random nature. So it has also following some probability distribution, that is called a waiting time distribution. That is known as the waiting time distribution. Why? Because the customer is waiting. How much time he is waiting? Is it exactly determined? No, it is uncertainty. Whenever there is an uncertainty component, there will be a theory of probability. So that this waiting time of a customer is always in random in nature, so that it having some probability distribution. That probability distribution is called waiting time distribution. Now my interest is we would like to derive the waiting time distribution. Agreed? Right. Let omega, what is the omega? Sorry, W. What is the W here? The waiting time of an arrival in the system. Why? Because waiting before it enters in the service platform. Is waiting because of entered into the service platform. He is expecting, he is demanding the service from the service station. Okay, so its value depend upon the number of units already waiting in the system and the service time ahead. Right? You are expecting the service from the service station. So how much time spending for service is 1 point, and the number of customers already waiting in the system. Right. So that is W. Now P and W. What is the P and W? Generally P stands for probability. Right. So probability that the waiting time of a particular unit in the time interval. Okay. W2 W plus DW. Note that the out of n units, n minus 1 units only waiting. 1 unit is existing in the service platform. Right. Now, if we derived that's a probability distribution, suppose n takes a particular value, n is equal to 0. Is a discrete number. So, now the system is empty and the first customer immediately take the service, so that there is no waiting time. There is no customer. Whenever the first customer entered into that, so whenever the first customer entered into the ATM counter, is necessary for waiting? No. Immediately go to the treasury machine. He doing his duties. He is doing his activities. Right? Okay. So there is no waiting time. There is no waiting time means W is equal to 0. That is nothing but probability that no customer in the system upon arrival, that is equal to P naught. So what is the P naught here? 1 minus rho. It is already derived. So whenever n is equal to 0, right, there is no waiting time to the customer immediately entered into the directly to the service platform, because there is no queue, so that no need to wait, directly go to the service platform, and that value is calculated as 1 minus row. Second case, suppose before entering myself, say at ATM counter, some people are waiting for the service, for drawing the money, withdrawing the money from the ATM machine, right? So n is greater than 0. N is greater than 0. I am waiting time. Here waiting. It is a continuous pattern, so that there existing a continuous probability distribution. Continuous probability distribution. So n greater than 0. Now this is equal to P n W. Here n greater than 0. Here n is 0. Agree with my point here? Right. So probability of the customer, one customer in the service time at DW. One of the customer at service platform. How many customers waiting here? N minus 1 customers in service W. Because W, DW is my time interval. W, DW, W plus DW. So that is a stationary independent increment process. So how many customers at the initial stage at the service platform at DW? Only one customer. How many customers in the existing in the rest of the interval here? Okay, n minus 1. Once again, that point is crucial for us. The time interval is W, W plus DW. W plus DW. So you may observe here W, W plus DW. Here that interval we may written as 0 to W, 0 to W, 0 W to W plus DW. W to W plus DW. So the total interval right now we may written as what it could be: one customer at service platform, n minus 1 customer waiting in the rest of the interval. Now one customer service rate, what is it? Mu into DW. Now n minus 1 customers waiting. So these n minus 1 customers is expected to arrive into the service station, so that it has a arrival process. It has the arrival process with respect to service platform. You remember that point. So arrival departure. Right now I am talking arrival departure from the queue. They are arrivals into the service station. Okay, so that will be a Poisson process. What it could be? E power minus mu t. Instead of t, we can write W into mu t whole power n minus 1. Right? N minus 1 factorial. You know that the arrival process. What is the arrival process? E power minus lambda t. Okay, lambda t whole power n by n factorial. Instead of t, we can write W, because waiting time is denoted by W. Okay, how many customers right now? N minus 1. So that e power minus mu t, lambda mu t into whole power mu t whole power n minus 1 by n minus 1 factorial. Agreed? Right. Now, my interest is the probability distribution of all the members, so that we submit. Summation n is equal to 1 to infinity. Why? Because 1 to n is 0 is already determined in the previous step. Right? So n is equal to 0, 1 to infinity Pnt, this term, into the probability of n units, its probability function. Probability of n units in the system. Okay, so this summation for all the customers, this is only for the departures of we are calculated already previous step and the respective probability function. Right? Now this term stands for, what is the term here? P mu into dw into e to the power of minus mu w into the M-type function into the probability function of that arrival. That is called steady state solution. You observe it. Summation as usual I am writing. This P and W this P and W is nothing but this term, okay, into dW and the respected probability function. What is the respected probability function? Is nothing but a steady state solution, that is Pn. That is Pn. What is the Pn generally? 1 minus rho into rho power n. 1 minus rho into rho power n. The same step again we are carried here. Again, instead of rho Pn, I am written as rho power n into 1 minus rho. Okay, here you remember this rho power n, possible to write rho into rho power n minus 1. Rho into rho power n minus 1. That rho taking outside because the summation running from n only. Okay, so here this term stands on rho power n taking outside, and here instead of rho power n I can written as rho into rho power n minus 1. That rho is also taking outside. Okay, now this mu is constant with respect to summation. Okay, and e power minus mu w, it is also constant with respect to summation. So what are the terms? Mu taking outside, e power minus mu w taking outside, here rho power n, rho 1 minus rho taking outside, here rho power n minus 1 into rho, that rho is also taking outside. So what is the remaining term? Summation n is equal to 1 to infinity mu into rho omega whole power n minus 1 by n minus 1 factorial into rho power n minus 1 into dw. The same step again I am writing like that. Are you okay na? Here rho power n minus 1, here mu into omega whole power n minus 1. Shall we write this rho inside the n minus 1? Yes, I am writing inside the n minus 1. Yes, this summation right now expanding n on n. Put n is equal to 0. Mu into omega into w into rho whole power 1 minus 1. So 0. 1 minus 1 factorial, 0 factorial. So this is, the numerator is 1, the denominator is also 1. Okay, next put n is equal to 1. Mu into omega into rho whole power what is it? N is equal to 2. We substitute 2 minus 1. So 1 by 1 factorial. Similarly, n is equal to 3. Here the numerator whole square by 2 factorial. N is equal to 4. The numerator whole cube by 3 factorial. Looking like that. Yes or no? Okay, right. For different values, it can be expanding as e power x. E power x. So instead of x, what is the term here? Instead of x, mu into omega rho w into rho. Instead of x, which term is existing? That is nothing but mu into w into rho only. That is, this summation is nothing but expansion of e power mu w rho. Agree? Yes. Now you can observe it here. E base is the common, so that minus mu omega taking the common 1 minus rho. 1 minus rho into dw. Okay, so this is a waiting time distribution of the customer in the model M1. This is valid for n is equal to 0 and n is greater than 0. Instead of n is equal to 0, here also I have made a there is n is equal to 0 here, is n is greater than 0. Again this point also note in our notebook. So not w here, n is equal to 0, n is greater than 0. Why? Because in the previous step just you can see that n is greater than 0, we derived it. Again the previous step stands for here n is equal to 0, we derived here n is equal to 0 as well as n is greater than 0. So what is the waiting time distribution here? The waiting time distribution PW is equal to 1 minus rho for n is equal to 0 and n greater than 0. This is mu into rho 1 minus rho into e to the power of minus mu omega into 1 minus rho only. 1 minus rho only. Agreed with my point? Okay, right. Now we need to calculate we need to calculate the average waiting time of an arrival in the queue. That is equal to expectation of W. Expectation of W. Now I changed the notation here right now. Instead of N, I can write W also. So that there is even no change for the year, because okay, you can write it, that is also W. We don't have any objection. The reason is very clear. It is the waiting time distribution. So waiting time distribution is always continuous function. So that you can write. So expectation of W. What is the expectation of W? Integral 0 to infinity W into the respective probability density function. So after simplification, okay, you will get this term is rho by mu into 1 minus rho. Mu into 1 minus rho. Okay. Otherwise, if you feel that it is an inconvenience to what I'm called integration, now there is a one formula actually proposed by one famous statistician, Little's formula. The Little's formula representing always the relationship between the expected number of customers in the queue, the waiting time distribution of queue. That is equal to LQ is equal to lambda into LW. What is the LQ here? The expected number of customers in the queue. What is the WQ here? The waiting time distribution of the customers in the queue. Right? So that relation LQ is equal to lambda into LW. So what about the LW? There one statistician proposed a formula. What is the formula here? The relationship between expected number of customers in the queue and waiting time distribution of the customers in the queue. W stands for waiting time. L stands for the expected number of customers in the queue, the averages. Okay, so by using this formula, it is already discussed in the chapter, the lecture number 1. Already it is discussed in the lecture number 1. The relationship between the relationship between customers in the queue and waiting time distribution of the customer. Okay, so LQ is equal to lambda into WQ. So WQ is equal to lambda q by lambda. Just we are simplifying that value. That is equal to lambda into mu by lambda by mu into lambda mu minus lambda after simplification. Similarly, by using Little's formula, the average waiting time of an arrival in the system. So that is the average waiting time in the queue. Now it is the average waiting time in the system. Average waiting time in the system. So S stands for system, Q stands for Q. Okay, the small letter Q stands for Q. Okay, WS is equal to LS is equal to lambda into WS. So by using this relation, WS will be simplified as 1 by mu minus lambda. Mu minus lambda. Are you okay? Right. So the operating characteristics of the queuing model we derived as 5 to 6 points. One point is the expected the probability of the queue size greater than n. The second one is the expected number of customers in the system. Third one is the expected number of customers in the queue. Right. Fourth one is the waiting time distribution. Okay. Now the fifth one is the expected number of or the expected and average. The average waiting time of an arrival in the queue and in the system. So LQ, LS, WQ, WS. These four are major operating characteristics. Major operating characteristics of the queuing model. Okay, so those formulas are much more important. Okay, you note that the students in a typical errors also existed in our lecture. Here instead of LQ you can write LS. Please note in our somewhere. Instead of LQ you can write as LS. Are you okay? Right. That will be interchanged. That's it. There is no other problem. Right. Model 2. In a model 2, M1 In the previous model, the capacity of the system is infinite. Right now, the capacity of the system is finite. That finite number is denoted by small n. The same Q discipline, first in, first out. Okay, so what is the difference here? The arrival time is as usually Poisson. The service time is as usually exponential. The number of service channels also only one. There only here instead of the capacity finite. So instead of infinity we can write small n. This is the only change. Right, again the service pattern, as what is the service pattern here? Service pattern here, first in, first out. Okay, by using the similar lines we can derive its steady state solution. Pn is equal to rho power n into 1 minus rho by 1 minus rho n plus 1 when rho not equal to 1. Again, if rho is equal to 1, 1 by n minus 1. What is the capital N here? What is the capital N here? The capacity of the system. The capacity of the system. Agreed with my point here? Capital N stands for the capacity of the system. Of course, no need of any derivative part. You remember it, because even the previous model also not much more interest about the derivative part. But the reason is, at least the primary model can be derived, all the operating characteristics, its steady state solution. It is helpful to the student, so that I am derived. Similarly, also we go through that the average number of customers in average number of customers in the system, LS is equal to this value, and the average number of customers in the queue, that is LQ. So 1 minus n. N stands for all the symbols right now explained. N stands for the capacity of the system. Rho stands for traffic intensity. How do you define the rho here? Lambda by mu. Are you okay na? The same things will be explained, okay, in the system with finite capacity. The same model with finite capacity. Are you okay? No need to derivation of these parts. Okay, if you are interested, you go through that, you verified any one of the reference book, because as for our syllabus structure, not need for derivation of a finite capacity of the system. Are you okay? Right. Before leaving, you note that all these points, the operating characteristics of the queuing model. Okay, first, the average waiting time of an arrival in the system, WS, is equal to 1 by mu minus lambda. The average waiting time of the queue, LQ, is equal to lambda by mu into mu minus lambda. The average number of customers in the system, LS, is equal to lambda by mu minus lambda. Similarly, the average number of customers in the queue, LQ, is equal to lambda square by mu into mu minus lambda. These things is enough for our applications. Okay. Now, again, what is it? The average number of customers in non-empty queue that forms from time to time is mu by mu minus lambda. Right. Similarly, what is it? The probability of number of customers in the system, or the system, no customers in the system, or the system is ideal. The system is ideal means P naught. What is the P naught here? 1 minus rho. What is the 1 minus rho? 1 minus lambda by q. So here lambda by q is called utilization factor. Sometimes you called as traffic intensity. So 1 minus utilization factor. Traffic intensity sometimes called as utilization factor. Okay. Again, probability that they're having n customers in the queue, already derived this point here. Okay. 1 minus lambda by mu into lambda by mu whole power n minus 1. Okay. More than n customers in the system, lambda by mu whole power n plus 1. Okay. Again, probability that there will be less than the customer, 1 minus of that. Okay. Similarly, all the points, finally you talk about Little's formula. What is the Little formula here? LS is equal to lambda into WS. LQ is equal to lambda into WQ. So this is the relationship between customers in the queue and waiting time of the customer. Are you okay? So these formulas, list of formulas is required for the solution of many problems in the coming class. many problems in the coming class. Are you okay? Right. Any questions? Just to here in this lecture, as per my side, there is just some typical errors. Just you check it once again. Okay. Thank you very much.